Okay, the first problem is this one. And it states the following. A bag contains 65 marbles of the same size. There are 20 red ones, 20 green ones, 20 blue ones, and another 5 that are either yellow or white. So let's just record this in some way. So you got a bag with marbles inside it, and you got 20 green, 20 G, 20 blue, or 20 red as well, and five which are yellow or white. Right, Ahmed removes marbles from the bag without looking. Okay, so he just keeps removing marbles from this bag. What is the smallest number of marbles that he must remove to ensure that he has 10 of the same color? Well, it's quite possible he can, by some chance, he picks up all greens. In which case, well, maybe 10 greens. His first 10 choices are all greens. That means he has removed 10 marbles. And you might feel that this is the smallest number, 10. But this is a very special case. He need not remove 10 greens. He can remove any of these marbles. All right? He's going to remove marbles without looking. And he can remove any number. Because you need to ensure, you see. So the question is now, you can keep, if you remove all 65 marbles, for instance, then you certainly will have 10 of the same color. But you want to know what the smallest number is. In other words, how many must you withdraw or draw from the bag in order to ensure that he has 10 of the same color? Okay, so the way to do this is to just look at the worst possible scenario where he's not drawing 10. He's just about to get there, but worst possible scenario. Okay, like for instance, he can withdraw, say, he wants to have 10 of the same color. So he can withdraw 9 greens. And he keeps withdrawing, he hopes he can get a green, but he doesn't. Instead, he gets 9 blues. And then he hopes now he can get a green or a blue, but it doesn't happen. It's really bad luck. Or he can withdraw 9 reds. And even here, he hopes that the next one will be a green, a blue, or a red. But instead, he suddenly lands up with those 5, yellow or red. And he withdraws all these. And he still has not got 10. But now this is the end of the line. Because the next one he withdraws will certainly ensure that he has 10 of the same color. Right? Can you see it? So the worst possible case is where he withdraws 32 and then none work. The 32 withdrawals, we'll call it withdrawals. I don't know why my writing is so. Okay, so to ensure that he has 10 of the same color, he has to withdraw one more. And that will guarantee that he will have 10 of the same color. It doesn't really matter whatever it is, but the next one he withdraws is going to be a green or a blue or a red. And then he has his 10. Okay, so this is the first problem. And now all these problems are very, very nice because there's very little mathematics involved here. Like here, you see, you're not using any quadratic equation or analytical geometry or anything like that. It's just pure logic. So even if you're in grade 8, you'll be able to, and if your logic is good, you'll be able to get this answer. Okay, so that's the first one. Let's get on to the next problem. Are there any comments from our participants? You can, if you want to comment, you can comment in the chat column. I can see it if you're commenting on the chat column, and then I can get David to read it, and we can answer it. All right, so let's get on. The next problem. Okay, this next problem is another interesting problem. All these problems are interesting. I love these logical problems, and I'm sure you do as well. But it's they're not easy. So that is why this session is very important. You can see how the thinking needs to be directed in order to solve these problems. Right? It's all thought processes involved here. So children at a school fun day had to guess the number of marbles in a jar. So you got a jar and a lot of marbles there, and these children have to guess the number of marbles in a jar. So you got a lot of all these marbles. It's a nice little competition. I remember when I was in school, they used to have these kinds of competition. How many marbles are there? I remember sometimes we used to actually go and get the marbles and try to put it into a jar and make an estimation. But that became a very costly business. So we have to estimate. It's an estimation to see how good you are. Anyway, Emily guessed, okay, the prizes were awarded on how close the guesses were. The first prize went to Emily, who guessed 125 marbles. Well, let's just put all these numbers on the number line, because that should help, I think. So Emily, she guessed 125, and she came first. All right, so she was closest to the correct answer. We don't know where the correct answer is, but she was closest. Okay, so that takes care of Emily. She came first. Then the second prize went to Cassandra, who guessed 140. Well, on the number line, 140 is further down. Yeah. She came second. That means Emily was closer to the correct answer than Cassandra, than 140. 125 is closer to the correct answer than 140. Now, can we kind of estimate where the correct answer should be? Yes, you can, because you take the halfway point between these two. Now, the halfway point between 120 And $140 is, you just add the two up and you get $132.5. All right, so let's take 132, because that you want it to be closer to Emily. So the correct, if it was 132, then this is 8 away and this is 7 away. So 132 is a possibility. In fact, any one of these, 131, 130, and so on, the correct answer is going to be in between these two. Well, rather, it's not going to be 140. It's going to be less than 132. We don't know where it is. It could be on this side as well. Okay, so if we say let X be equal to the number of marbles, then certainly X is less than or equal to 132. I don't know where it is. It's maybe on that side. But certainly X is not here. Right? X is closer to 125 than 140. So X is one of these. Okay, let's look at what goes on here. Now the third prize went to Sigrid, who guessed 142. This was third. And the fourth went to Rina, who guessed 121. So she's fourth. So 142 is closer to the answer than 121. Closer to X. X is the correct one. Then 121. So like what we did before, what can you say about this? The halfway mark, 121 plus 142 is 263, is 131.5. So this is closer. So 132. Well, again, you have 132. So it's the distance between 132 and 142 is 10. And from 132 to 121 is 11. So she came third, he or she came fourth. So the X that you're looking for is greater or equal to 132. It must be on this side, because she came third and she came fourth. But now you have these two things, you see. So very beautifully, by just looking at the logic of this, you can see that the number that we're looking for is greater or equal to 132. It's also less than equal. There's only one number which satisfies both of them. So the number of marbles, this is supposed to be an exclamation mark, because I've expressed the answer ecstatically. So this is a very nice problem. If you know just the first, second, third, and fourth, you can say, without knowing the number of marbles, then you can actually say exactly what the number of marbles is. Nice problem. Okay, any comments on that? Sometimes you might have you tried this thing out and you had an alternative solution, and you're quite free to discuss that alternative solution so that you can all benefit. Okay, so I think looking at this problem now. So here we have a pretty long story. 10 strokes 7 means session 10 problem 11. I had actually constructed 12 sessions originally. So I had 120 problems or even more. And then we started this whole program a little late, and we said, okay, let's try to do it in 10 sessions. And so I had to readjust this to get problems in 10 sessions. And again, it had to be reduced to 9. So that is why in your in your book of problems, you've got 10 sessions. Not sure, maybe you got 11 or 12 as well. But there are at least 10 sessions. But we only have 9 meetings. So I borrowed some questions from session 10. So 10 / 7 means this is problem number 7, session 10. Just for your information. Okay, Jack, John, and James are identical triplets. It is impossible to distinguish them by appearance. Right. Jack always lies. So Jack is a liar. But John and James always speak the truth. They are the truth tellers. Now, this is always, no matter what he says, it's a lie. And these guys also, no matter what they say, it's true. So that's very important. Okay, now you know that the triplets are between 20 and 30 years old. 20 and 30 included. So they all have the same age, obviously. So if the age is X, X, then they are between 20 and 30 years old. So the X is bigger than 20, but less than 30. So this is how we write this down. X lies between 20 and 30. It's less than 30, but they say it's 20 and 30 included. So we can put an equal sign here. That means X could be equal to 20, could be equal to 30. So this is a nice way of expressing X, but you must remember, X is an integer. So the only 30 minus 19, 11 numbers here, 20, 21 up to 30. Okay, so we got an idea of what the age will be. One day you meet 2 of the triplets and ask them how old they were. Okay, so you meet 2 of these guys. You don't know which 2. So they could be both could be speaking the truth. Or you can't have both speaking lies because only Jack, there's only one liar and 2 truth tellers. So you meet 2 of them. So one has to, either both of them are telling the truth or one of them is truth and the other is lie. So that's quite important. The fact that they say that there's only one person lies, it's useful to make some conclusion when you meet 2 people. All right. Now, A says, we don't know whether he speaks the truth or what. A says, we are between 20 and 29 years old. 20 and 29 included. So this is what A says. This is we are between 20 and 29. I'm going to put a question mark here because we don't know whether A is speaking the truth or A is a liar. But this is what he says. 20 and 29 included. I can put the equal sign to say X could be 20, could be 29. Now B makes the following statements. B says, we are between 21 and 30 years old, 21 and 30 included. So B says the following. Now, even this too, we don't know whether this guy is speaking the truth or what. But he also says one of us present is lying. What am I writing is really weird. Um, one of us is lying. He says that. Okay, and he says one of us. Now, he may be lying. He may be speaking the truth. So is B lying or is he speaking the truth? Let's look at B. Is B a liar or is he a truth teller? Okay, let's just assume for the moment that suppose B is a liar. B says one of us present is lying. So is he a liar? David, can you just open it up so that everybody has a chance to speak? I want you to think about this and tell me whether B is a liar. Okay, we got 11 people here. That's very nice. Now, is there anybody who wants to say something? You can put your hand up. The question is B a liar? Anybody wants to? Nico, you want to answer? No, that was my hand. Mm, nobody? Not a single person wants to take a try? Even in the chat, you can say yes or no. Oh, all my stuff got wiped out. Okay, that's the danger. All right. So let's just record what we had. A says we are between 20 and 29. There's a question mark around him. And B says that is between 21 and 30. X is the correct age. The question mark around that as well. But now the question is B a liar? All right. Now, if B is a liar, then everything he says is a lie. Like what he just said now. Then it is a lie that one of the two is lying? Because he says so. B says so. It must be a lie. But this is false, because if B is a liar, then one of the two is a liar, namely B. And that's not a lie. No, that's the truth. Because if B is a liar, then it is true that one of the two is a liar. But he says it is a lie that one of the two is lying. So there's a contradiction here. So this is a contradiction. But it is true that one of the two, namely B, is lying. Is a liar. So this is a contradiction. You can't have a statement which is true and false at the same time. So what went wrong? What went wrong is the assumption that B is a liar. There are only two possibilities. Either B is a liar or B speaks the truth. So therefore B speaks the truth. Or he is the truth teller. Let's put it this way. Rather than saying he speaks the truth, he is the truth teller. That's what we want to say. All right, so everything that B says is true. And then B will be, like for instance, B said one of them is a liar. So therefore, it is true that one of them is lying, but so the other person, there's only one liar. So the other person has to be, so therefore A is a liar. Right? B is speaking the truth, and it is true that one of them is lying. He is not lying. He is speaking the truth. So A is supposed to be the liar. All right, so now you've got, so this is a lie. So this is false. Because A is a liar. B is a truth teller. This is true. So the other statement he makes is true. All right, so if this is false and this is true, what must X be? That's another interesting question. So it is false that X lies between X satisfies this condition, and it's true that X satisfies this condition. Okay, let me open it out again to you guys. Most of you people are practicing silence today. I would imagine that you would be able to reason it out. Don't feel shy. Nobody can see you, so you can only hear your voice. Anybody wants to say what X is? I'm suggesting that now we can actually decide what X is.
Sorry, sir.
Yes. Yes, Aiden.
So I think X is 30, sir.
Yeah, that's okay. That's the correct answer. And Hayden, can you explain why?
So if A is the liar and B is telling the truth, sir. So when A says that they are between 20 and 29 included, and that's a lie, then they can only be 30.
Yeah, well, a little bit more. It can be 30
And
or more, or
so it
19 or
says
less.
we know the triplets are between 20 and 30 years old. So if
Oh, I
B,
thought we know that. Okay. Actually, it wasn't necessary to give the statement, but if that wasn't given as a statement, even then we can make the conclusion. Okay, so you are quite right. So X, they are between 20 and 30, right? So X has to be 30, and that is, yeah, okay. All right, Hayden, while you're on the line, suppose we didn't know that. I'm suggesting to you that you can still conclude the same thing. Can you tell me why?
so A is lying by saying they're between 20 and 29. So then
Yes,
they could be above 29 if that wasn't given. But then B is telling the truth and says they're between 21 and 30. So if they're not
yeah,
between 20 and 29, but they are between 21 and 30, then it has to be 30.
that's right. Uh, but the false statement here is not only that X is greater than 29, but X could also be less than 20. That's also possible. If this is false, then the age could be either greater than 29 or less than 20. Two possibilities, right? X less than 20 is not possible because of this. This is true. Okay, you agree, Hayden?
Yes, sir.
Yeah. So the falsity of this means that X is bigger than 30, greater or equal to 30, or X is less than or equal to 29. On that, you can see it clearly on the number line. You put 20 and you put 29, and X is all over here. Maybe this. So if X is not here, then it's either here or there. You see? That is what we are saying. Well, thank you very much, Aiden, for making that contribution. I'm very pleased that somebody contributed towards the answer today, and I hope others will also participate a little later if the need arises. Thank you. So let's go on. Hope I'm not missing out anything. Yeah. Okay, this is the one. All right. In a soccer tournament, each of the 6 teams played with other teams exactly once. At the end, the team scored 12, 10, 9, 8, 7, and 6 points, respectively. How many points are awarded for a win if a draw earns 1 point and a loss earns 0 points? Okay, now this is quite a mouthful. I have to admit that it took me a little while to get to the answer here. And here we're going to have to use a little bit of mathematics. Okay, so there are 6 teams. I've drawn a grid here to say, okay, let's just write down the table, the points table. I presume that all of you have seen a points table at some time or the other. So you've got the 6 teams. They're playing with each other, and each of the 6 teams played with other teams exactly once. Well, I'm going to put a cross here, but A obviously can't play with it itself. Now these, an arrow like that says that A plays A, B plays B, C plays, A plays any one of them. So the scores, we're going to put the scores in these squares here. Right? Or we can put either a win or a loss, or we can put scores. Okay, so There can be no scores, yeah. So how many games are played? So you have A plays, there are 5 here. Now, A plays B, whatever the score is here, the same score will have to go in here because B plays A is the same game. These are the two teams. So whatever number I put here, suppose A plays B. Oh, wait a minute. Suppose A plays B, and if this is a win, then here I'll have to put L. So B lost to A, but A beat B. I've got the arrow like that. Okay. So if I got a W here, I'll have to put an L here. I hope you understand that. Right? Because in the game between A and B, if A beat B, then I'll put a W here. But then B lost to A, so I'll put an L here. Right? So in these squares here, you have won or lost or even drew. It's possible they can draw. So the games are, you only have, these two represent the same game. Right. So the games that you have are where A plays B, A plays C, A plays D, A plays E, A plays F. So there are 5 games here. And you don't count this because A plays B, we already counted. Right? So you count 4 here, and 3 here, and 2 here, and 1 here. So altogether, the number of games from this table here, you can see it's going to be 5 plus 4 plus 3 plus 2 plus 1. And that's 15. The other way of doing it is, or to count the number of games, right? Or pick 2 games, pick 2 teams, from 6. What do I mean by that? If I want to identify a game, all I have to identify who are the 2 people who are playing in that game. So each time I pick 2, that's a game. So the number of games is equal to the number of ways you can pick 2 teams from 6 teams. It's the same number. Each time you pick 2, you get a game, and every time you have a game, you have exactly 2. So, and we know this. In how many ways can you pick 2 objects from 6 objects? We've seen this many times. It's 6 times 5 divided by 2. N into n minus 1 over 2. The number of ways in which you can pick 2 objects from n objects is n into n minus 1 over 2. We've seen this many times. And the number of ways of picking 3 objects from n objects, we've seen this too, is n into n minus 1 into n minus 2. And here you have 1 times 2 times 3. Right. So these are important formula. If you want to pick 4, n into n minus 1 into n minus 2 into n minus 3, you have 4 factors starting from n. And at the bottom, you have 4 factors also. But there you start from 1. So, and there it is. This is 15. But we can actually see what the 15 games are. All right. Okay, so let's just remove all these things. Okay, now we know there are 15 games. So at the end, the team scored 12, 10, 9, 8, 7, and 6. Okay, suppose we just put these. So suppose A came first. I can always do it like this. Like 12, 10, 9, 8, 7, and 6. So the team called F scored only 6 points. Now here you can put numbers here, whenever there is a loss, it's 0, or when there's a win, we don't know how many points are awarded for a win, and how many points are awarded. Well, for a draw, it's 1 point. All right, now where do we start here? Right. Now we do know that every time there's a W, there's also an L. Okay, so suppose now there are X wins in this table. Suppose in the table, you see you got we have something like this. This table is filled, something like that, right? With win and loss, win and loss, win and loss. And but if there's a win here, then there's a loss here, right? A plays C, A lost to C, so C won. So there's a W there. So A beat D, so D lost. So every time you have a W on this side, you have an L on this side. Right? But it could be a draw. Like for instance, I could have had a draw here. C played E and it's a draw. Then E played C. That comes here. So that's a draw. See? So if there's a draw there, then you got the same thing here. But if the W here, you got an L here. So this is what the table looks like. Let's get an understanding of this. Let me take all these things out. All right. Now, I don't know how many W's there are in this thing, but suppose we've got X W's. Suppose the table has X wins. X wins. Earlier on, I put a W. Right. So altogether, you've got X wins. It could be a W here, it could be a W there. But then there are XLs also. There are also X losses. Right? Because each time there's a win, there's a loss also. So the wins and the losses account for 2x of these entries. But you have, in addition to W and L, we saw there were draws also. Hence, how many Ds are there? How many draws? Well, okay, every one of them. A game is either it's got a W or a L or a D. Every game, there will be a decision, right? So the XWs and XLs in this, and how many of them are Ds? All right, I'm going to open it up again. How many of these squares are Ds? Anybody wants to answer? No one? All right, so every one of these blank squares are filled. You got 15 on this side, blank squares, and likewise you got 15 blank squares in this side, right? So there are 30 blank squares altogether. And in this, but they all 30 of them are actually filled with either are filled with W, L, or D. Right? Now we've already got XWs and we got XLs, so that makes 2X. Altogether, you got 30. So there are 30 minus 2X draws. And only one unknown. That's very nice because we have so many possibilities. You know which is W, which is L, which is D. But if you count just the number of W's altogether, then there are also the number of L's is the same thing. And you know altogether you got 30 squares which need to be filled. 2X are filled with L and W. The remaining ones, which are 30 minus 2X, has to be filled with draws. Right, now we can count the total number of points. Okay, now we know that a win, we don't, how many points are awarded for a win? Now that's a question. So we need to give a name to that. Suppose a win gains or is awarded well, we don't know what it is. We call it N points. So each time there's a win, you get an N, right? So every time there's a W here, we can place, if I got to say W, L, L, D, W, for instance, then I'll have to put N here because there are N points for W, N, and the draws will be 1, and this will be 0. Right. So now I can replace these tables here just with the number of points that they have. All right, so let's count the total number of points. Total of all points. Hope that's understood. All right, you've got XWs, and each W has got N points in this. So you'll have NWs. So wherever I got a W, I've got an N there. So I'm now got a number. We don't know what N is. It could be 3 or 4, whatever. Right? I'm sorry, this is NX because the X, the XWs altogether, and each W is awarded N points. There are also XLs, but the L's score no points. This is for the L's. And there are 30 minus 2X draws, and each draw carries 1 point. So if you add up all the numbers here, like for instance, I got N and 0, 0. If I add up all that, this is what I'm going to get. Right? But we know what they all add up to. It's 12, 10, 9, 8, 7, 6. Right? So it's 22, and 9 is 31, 39, 46, 52. So this is 52. Okay, I need space now. So we've got an equation here, an interesting equation. The equation reads the following. Nx plus 30 minus 2x equals 52. This is what I'm rewriting, right? 1 times this is itself. 30 can be brought to the other side, and you have nx minus 2x is 52. I can take x out as a common factor. So you have x into n minus 2 is equal to 22. So now you have an equation, but with two unknowns. So it's quite beautiful. This problem solving is very, very nice. This from a thing like this now you can actually get an equation just using common sense and knowing. Right, so you've got x is, just remember, x is the number of wins, and n is, we are looking for the number n. We want to know what is n. Right? And both of them are positive integers. Right? The number of wins. X could be 0, but obviously x times something is 22, so x is not 0. So what are the possibilities for x? X is equal to, this is a whole number, that's a whole number, and n can't be 2, but n must be greater or equal to 2, greater than 2. So n is going to be a number which is greater or equal to 3, because it is n minus 2 has to be positive. You're multiplying a positive number by something to get 22. So the number of points which are earned is at least 3 points. And is, so at least that's very good. You know, and is, and it's also a factor. You see, n minus 2 is a factor. That's very powerful because these two numbers multiplied gives you 22. So there are very few factors. So what are the possibilities for n? So n minus 2 has to be, it's going to be a factor. So n minus 2 is greater or equal to 1. Okay, that doesn't help you too much. So n minus 2 is equal to 1 or 2 or 11 or 22. There are only 4 factors for 22. Right, then if n minus 2 is equal to that, then the product of these two, so x in that case will be 22 or 11, 2 or 1, because x times this is 22. So, right. Now, x is the number of w's in this table, right? Well, this is the number of draws. Equals 30 minus 2x, if you remember. Now you can't have x equals 22 now, because then you'll have 30 minus 44, which is negative. That's not possible. Now you could have x equals 11, and then in which case there are 8 draws. 11 times 22. That's possible. Now x equals 2 tells you that n equals 11, so n will be 13. So the number of points for a, you see, if x equals 2, then n is equal to 11. N minus 2 equals 11. in which case n is 13. Now, you can't have 13 in any of these rows because the largest possible sum, you're adding up all these to get the number of points A has scored. N cannot be 13 because they all add up to numbers which are smaller than 12. So even this is out. Right? And for the same reason, you'll have x equals 1 is out. Also because then n is equal to 24. So there's only one possibility. Okay? So from this equation here, you can take all the possibilities and you can eliminate those just by looking at the table and understanding what the problem is. So you got x is equal to 11, and therefore, if x is equal to 11, then n minus 2 is equal to 2, and n is equal to 4. And that's the number of points. The problem was to find n. So therefore, a win counts n points. Very beautiful problem. You should go and logically try to figure out how to work it out again on your own. Because there's a lot of little things here, but they're all thinking. They are all logic. And you have to look at the information and somehow eliminate, say, if this happens, this is not possible. If this tries, that's not possible. And slowly you zoom in on your correct answer. See? So it's a very interesting problem. All right, any comments here? Okay, so let's just get on to the next one. Okay, so here you got 5 circles overlap in 9 regions as shown. Okay, certainly there are 5 circles. Let's have a look at the circles here. You got 1, 2, 3, 4, 5. Okay, there are 5 circles. There are 9 regions. This is a region. So you got 3 plus 4 plus 7 plus 9. Okay. Place one of the numbers from 1 to 9 without repetition in each region. So these regions, you place the numbers 1 to 9 so that the sum of the numbers in each circle is 11. Right? Wow. All right, in other words, if you add those two numbers, you get 11. If you add there are 3 numbers, yeah, that's 11, 11, 11. Okay, so the numbers in each circle is 11, and you got 9 numbers. How do you place them? Now, there are so many ways of doing this, but each time you have to ask yourself whether you are adding up to 11, right? And you're not allowed to repeat. You have to put all the numbers from 1 to 9. So this is an interesting one. A lot of people try these things, but what they do is by trial and error, they eventually get to the answer. And it may take a bit of time. But I suggest to you that you can actually calculate. Interestingly, you can calculate these 9 unknowns. Very beautiful. Now let's see how can I calculate these 9 unknowns. Well, for a start, the numbers are 1 up to 9. So the sum of all the numbers is 1 plus 2 plus 3 up to 9. And that is 45. By now, you should know that if you add the numbers from 1 to 9, you're going to get 45. All right. So when I add the whole lot of these, I get 45. But now you know that each of these adds up to 11. So all the circle numbers sum to 55. The 11 sum to 11 times 5, which is 55. In other words, if I add those three, those three, those three, those three, because it's 11, 11, 11, 11, 11, it's 55. So why do you have more numbers than 45? Right? So they all add 55. The reason why you got extra is because these numbers here are counted twice. B, D, F, and H, those numbers, they are counted twice. This is counted here in these two circles. Again, it's counted in these two circles, counted in these two circles. So each one of them is counted twice. Those are the only ones which are counted twice. None of the others are counted twice. So these are the sum of these contributes to that extra that we have, 55, right? And we had 10 more. And where did the 10 come from? It came from the fact that coming from this. This is a very important logical conclusion. Now, you got the numbers are coming from 1, 2, 3, 4, 5, 6, 7, 8, 9, and you got 4 numbers adding up to 10. And there's only one way you can do that. It's the first 4 numbers. The 4 smallest numbers add up to 10. So the conclusion is that these numbers here, B, D, F, and H, they are, we don't know where they are situated, but they are 1, 2, 3, and 4. Could be 2, 1, 4, 3, or 4, 2, 3, 1, or whatever. But we know that that collection is has tens in it. And so you still got the remaining, the remaining 5 numbers are in the outside regions. A, E, I, C, and G are coming 5, 6, 7, 8, 9. All right, so where are we going to place these numbers here? You can see one interesting thing is that there are only 2 numbers here. They add up to 11. And B is one of these, 1, 2, 3, 4. So if B is 4, then A is 7. If B is 3, then A is 8. And if B is 2, this 9. And B is 1. Or B can't be 1, because then that is 10. Right? So this is out here. B can't be 1, because then that will be 10. And we only have the numbers from 1 to 9. So that is out. No. Wait. I'm saying B cannot be 1, but B could be 2 or something like that. So I shouldn't scratch the thing out. Okay. Okay, so let's, we want B to be as small as possible. So let's try B equal to 2. So this will be 9. All right. Now, so what else can we say? If we Uh, okay, I'm not too sure what to do here. Let me go look at the answer. I have I know these four numbers add up to 10. Okay, let me look at the answer. I've done this some time ago, so I can't remember exactly. Anyway, how do I scroll upwards here now? I've hardly ever looked at these answers while I teach, so I'm not sure what to do here.
Yes, yes, I can see that.
All right, okay. So what I've said here is that C, the next one is C plus G plus 10. You see these four numbers add up to 10, right? B, D, F, and H. So when you add those 10 together with C and G, you're going to get 22. Because these four add up to 11, 11, 22, and those four add up. So C plus G must be 12. So that was the thing that I was missing. Now, if C plus G is 12, then there's only one way you can get 12, and that is it's 5 and 7, right? Because you got 1, 2, 3, 4, and you got 5, 6, 7, 8, 9, 10, 5, 6, 7, 8, 9. And which two numbers from 5, 6, 7, 8, 9 add up to 12? You get 5 and 7. So we know that this is 5. Maybe this is 5 and this is 7. Or you could have 7 and 5. Okay, so I had 2 and 9. And I could have had 7 and 5. All right. But if I had 7 here, that wouldn't work because remember, I put 2 here and I put 9 here. Then I will have 7 plus 2 is 9, and this will be 2. So we're not allowed to repeat. So 7 can't go in here, only 5 can go in. So once I got 5 plus 2 is 7. This has to be 4. All right, and this is 7 here. So now we've got quite a few of the numbers in. I got 2 and 4. So you got only 1 and 3 left here. Because these two are chosen, and we've got A, B, C, D is from 1, 2, 3, 4. So we only have 1 and 3. Can I have 1 here? If I had 1 here, then I got 7, 1, 8. I can't have 1 here because then I'm going to have 10 here. And I don't have 10 available. So 1 and 3 go in here. 1 can't go in here. So it has to be 3 here. So once I put 3 here, then that automatically becomes 8. And this is 1. And that gives you 11 here. And 4 and 1, 5, 6 will go in there. Okay, so I hope you follow that argument, but the starting point, which I missed, was that these two add up to 12. Right, and that is a crucial point, and I missed that one. Okay, so let's go back to the next problem. Okay, so logically, you can actually solve this problem. Now, oh yes, assignments. You got 2 assignments for this week, so it's going to be a little bit challenging. And because last week you were given a break, and I mentioned last week that you're going to have 2 assignments this week. If I think I did, and these are the 2 assignments. You can try them out. Okay, so now we get on to the next problem. All positive integers greater than 1 are painted in 2 colors, blue and red. Now, that's a lot of painting to be done. So you got every number is painted. So I'm just trying to get my okay. So you got all the numbers from the greater than 1. They are the positive integers. So, okay, that's useful to know. Not every possible number. So you've got 1, 2, 3, 4, and so on. Every one of them is painted, and there are 2 colors, either blue or red. So this could be blue or red, blue or red. So every number is painted. It is known that the sum of any 2 blue numbers is blue, including the sum of 2 equal blue numbers. All right, so the sum of any 2 blue numbers, if I had, for instance, if I had 18 is blue and 37 is blue, then 50, so is 55. The sum of any 2 blue numbers is blue. And the product of any 2 red numbers is red. So if I had 5 and 7 are both red, then it implies that 35 is red. Okay. So now it says it is known that the number 1024 is blue. And there is at least 1 red number. Now, how many numbers greater than 2000 and less than 2024 are red? This looks like a very hard problem. When you see the solution, you see how beautiful it is. All right, so let's have a look at this now. The starting point is knowing that the sum of any 2 blue numbers is blue. Now, let's just ask about 1. One could be blue or red, but you can't make any conclusion with that. But let's try 2. Now, is 2, you see, we know that 1024 is blue. Now, 1024, those of you are familiar with numbers will know that 1024 is 2 to the power of 10. Right? When you factorize 1024, you can only choose, right? So now can 2 be red? Right? If so, the product of any 2 red numbers is red. So if so, then 2 times 2 is red. Multiply by 2 again, because that's red. Multiply that by 2, it's red. And you go all the way up to 2 to the power of 10. And that is red. And that's a contradiction, because it is given that 1024 is blue. So the question is 2 red? The answer is, if it is red, you got to get to a contradiction. So the conclusion is that therefore 2 is blue. So this piece of information can be used to conclude that 2 is blue. because it is 2 multiplied by itself several times, it can't be red. Okay, now the sum of blues is blue. So if you're adding 2 to itself any number of times, you're going to get blue. So what does that mean? Therefore, 2 plus 2 is blue. 4 plus 2 is blue. All blue. So in other words, all the even numbers are blue. So we now come to the conclusion that all even numbers are blue. In particular, oh yes, now this asks how many numbers between 2000 and greater than 2000 and less than 2024 are red, but you know all the even numbers in between are blue, right? So now we don't know anything about the other numbers, the odd numbers. All right, so let's see now, but they tell you there is at least one red number. How are you going to use that? Okay, we'll come to the conclusion. We used all these pieces of information, and we'll come to the conclusion that all the even numbers are blue. Now we're going to try to see how we're going to use the fact that there is at least one red number. Now, let's look at 3. Is 3 blue? We got 2 is blue, 4 is blue. Now the question is 3 blue? It's greater than 1, eh? So this is not counted. I was just worried about that for the moment. So we're not counting this. It's only from 2 onwards. Okay, is 3 blue? Now, if 3 is blue, suppose it is, then it means 3 plus any even is blue. Because all the even numbers are blue. And that's a problem. Okay, if 3 is, and any even number is blue, that means everything is blue. Because you can add 3 plus 2 will give you 5. You take any odd number, say 2019, right? This is 3 plus 2016. Right? If you take away 3 from an odd number, you're going to get an even number, and that's blue. So we just said 3 plus any even number is blue, so this is blue as well. So all numbers are blue. All are blue. But they say there's at least one red number. So this, if we make this assumption, then you get to an impossible situation, right? It's a contradiction. Because you are told there is at least one red number. So this question here, is it blue? If you say yes, you get a contradiction, therefore 3 is red. Three is red. We don't know what happens to a red plus a blue. We don't know. We only know red times red is red. Okay. So now let's take any power of 3 is red. I want to take a power of 3 which is greater than 2024. And we'll see just now why. Then 3 to the power of 3 to the 6 is 729. 3 to the 7 is 2,187. And this is red. I'm looking for a number beyond 2024, and that is red. Okay. Now, so that is red. Now let's look at 2021 or 2001. Now, is this blue? If this is blue, then 2001 plus, what must you add to this to get this? 186 is blue. Because this is even, and this is blue. But we just said that this is red. So this is false. So the question, is 2001 blue? It leads to a contradiction. So therefore 2001 is red. But then you can do exactly the same argument for the other numbers between, we're looking at the numbers between 2000 and 2024, all right? So you can do exactly the same thing, and you will see that you get, at the end now, we have the following. We look at the numbers between 2000 and 2000, greater than 2000, 2001, 2002, all the way less than 2024, 2023, right? Now we saw that this is red and this is blue. And as we saw again, you can use the same argument to get this is red. So you get red, blue, red, blue, red, blue, until you come to red here. So all the odd numbers are red and all the even numbers are blue. And in this slot, how many? The question is, how many numbers greater than this are red? So it's all the odd numbers between them, right? And if you count all these odd numbers, I think you're going to get 12. There are 12. So how many, the question is how many red numbers are there? And if you count them, you'll see it's 12. Okay. Now, that's we're almost at the end. I'm sorry, as usual, I just go on. And some people have left already. But just for the benefit of those people who are still here, let me have a look at this last one. Oh yeah, this is a tricky one. Okay, a mathematics competition consists of 30 multiple choice questions. I'm sorry, so 3 people have left. There are 8 of you left. I'm going to take advantage of this fact. Now, 4 marks are awarded for the correct answer. So you got multiple choice questions, MCQs. If you go to the correct answer, you're given 4 marks. But if you choose an answer and it's wrong, you get -1 marks. So this is negative marking for multiple choice, which is a wise thing to do. It avoids guessing. And if people wrote a blank answer, then you get 0. Now here's the question: what is the minimal number of participants needed to be sure that 2 of them will have the same score in the competition? Right. So this is very similar to that marbles problem that we had earlier. What is the minimal number? So what we need to do is we need to find out how many different scores are possible. And how many scores. A score, a score is the total marks. Scores are possible. Because if you know that, suppose we say there are only 49, this is just for the sake of argument. Suppose the answer, suppose we know there are 59, then there are 59 different scores. So the minimal number of participants will have to be 60 then, because then if you got 60 people and there are only 59 scores, then two of them will have the same score, right? Because all you have to do is to add one more, and then you got 60 scores, which are placed into 59 scores placed into 60 lots. So two of them will have the same score. So if we know this, then all we do is just add one to it to get the answer to the question. So how many different scores are possible? So let's just see what are the possible scores. Now, the lowest possible score you can get is minus 30. Right? And that's possible because you can get all negative ones. Right? You got 1, 2, 3, 30 choices, 30 questions. Now you can get a person really bad because everything he tries, guesses, and he gets -1, -1, -1. Extreme case. Right? But it is possible to get 30 -1s. So minus 30 is possible. And likewise, minus 29, in which case he says, okay, I'm not going to take a chance in one of them, but he'll get minus 29. So he can get several blanks, but you can see all these are possible. Even 0, because you can just give in your paper without answering anything, in which case you get 0. So all these are possible. Okay, so what else is possible? I suppose even 1 is possible. You could have 4 and -1, -1, -1. Right, and all the others 0. That gives you 1. Or you could have 2, you could have 4, -1, -1, and all the others 0. Or you could have 3, 4, -1, all zeros. And 4, when you have 1 correct one, and all the others 0. So a lot depends on how many negative ones you're going to choose. Okay. Now, 5, you kind of have 4 plus 1. So you'll have 4. And the 1 you can replace with this now. 4 -1, -1. That's 8 minus. Right. So you could go to 6. So actually these 4, they form a kind of a prototype. So each time, the first 4, you can get any one of these 4, and then you can get any one of the next 4 by simply just repeating 4 to the so these are either multiples of 4, like these are multiples of 4. So 4m is always possible. Right. In other words, you can get the score of 4 if 1 is right, and 8, 12. You can go all the way up to 30, where you get a whole lot right. Right. So all these are possible. So all the multiples of 4 are possible. We get so many right, and then you get zeros. No, you don't. You don't. You have blanks. You don't guess. And these are the non-guessing ones. Okay, now let's try, because we are breaking it up into fours, we now take a multiple of 4 and add 1 to it. Now these are the numbers we are looking at now. Whether you can get 5 and 4 plus 1 is 5. Keep adding 4. 9, 13, and you have 116. Say 112, 113, and 117. Right, now we want to know, is 4m plus 1 possible? Well, 4m plus 1 can be obtained by taking 4 into m minus 1, 4m minus 4, or otherwise 4 into m plus 1 minus 3. Or otherwise plus 3 times minus 1. Right. So you can get 4m plus 1, like what we did there. But you have to adjust how many 4s you need to have. How many negative 1s do you have? So you get 4m plus 4 minus 3 gives you that. So, but here now, how many questions are answered here? You've got 3 of them will have. So here, in this case here, you got number of questions. You got m plus 1 4s, and you got 3 negative 1s. But the multiple choice, you only got 30 choices. So you got, that sum has to be less than or equal to 30, because you are saying that m plus 1 are correct and 3 are wrong. So you'll have to have m plus 1 plus 3 is less than 30, which makes m to be less than 26, right? I'm just going to remove all this other stuff here. And let me just say what I'm saying here. I can say 4m plus 1 is always possible because that's what I got here. You can get m plus 1 correct answers and 3 negative answers, provided m plus 1 plus 3, the total number of questions you answer is less than 30, which is m less than or equal to 26. Okay, so that means now I can put any number less than 26. That's possible. So you'll have m equals 1 will give you 4 plus 1 is 5. You keep adding 4s here. 9, 13. The last one you come to is 26 times 4 is 104 and 105. Right. Now these are all possible. But 109, 113, and 117 are not possible. Because the largest one, the last value for m is 26, right? And 26 times 4 is 104 plus 100. This is the last one that is possible. So 4m plus 1, 3 of them, these, you try your best, you'll never be able to get these scores. All right, now these are the numbers which leave a remainder of 1 when you divide by 4. We've looked at the multiples of 1, and we looked at the multiples where the numbers leave a remainder of 1, and we found that there are 3 which are not allowed. Okay, and then we can continue to do the same thing. Yeah, let's look at those which leave a remainder of 2. and see what happens there. That will allow us to tell us which numbers which leave a remainder of 2 are not allowed. So you make the same kind of a calculation here. 4m plus 2 is 4 into m plus 1. So you get 4m plus 4, but now it's minus 2. Right. So 4m plus 4 minus 2. And here the number of questions is equals m plus 1. And this is plus 2 times minus 1. So you got 2 wrong questions. So you got m plus 1 plus 2, which is m plus 3. And as before, you want m plus 3 to be less than or equal to 30. And this time you have m less than or equal to 27. And you got 4m plus 2. So all these numbers, m equals 1, will give you 6. I'm sorry, 6. Keep adding 4, 10, 14. Right? And the last possible m value is 27. And so 27 times 4 is 108. So you come to 110. And that's the last one. So the ones, if you keep adding 4, you're not allowed to put, I mean, you can't get these 2 scores. Those 2 scores are not possible. And likewise, if you look at 4m plus 3, that's the last one. The only way you can get remainder, you can get remainders 0, 1, 2, or 3. And this is 4 into m plus 1, but minus 1. So it's plus 1 times minus 1. 1 wrong answer, and 4 m plus 1 correct answers. So this gives you m plus 2 questions altogether. And this time you have m is less than or equal to 28, just like before. And the last possible number you can get is 28 times 4 is 112. That's 115. These are all these numbers. 7, 11, 15, all these. Going up to 115, m equals 28, but 119 is not possible. So the numbers which are not possible are those which are ringed here, right? Which means there are only 6 numbers from minus. Let me just summarize all this now. So we got the 6 numbers which are not attainable, right? Now, how many numbers are there altogether from minus 30, the lowest, to the highest, 121, right? The highest possible number you can get is 120. So it's minus 30, minus 29, all the way up to 120. That set has 151 elements. Because you got from 0 to 120 is 121, and then you got 1 to 30 is another 30, so that gives you 151. And 6 not attainable. Leaving 145 different scores. So the number of different scores which are attainable is 125. From the 151, 6 are not attainable. And therefore, the minimum number you need to have, minimum number of participants has to be 146. Because then you can be sure that 2 of them will have the same score. Okay, so that's a kind of tricky problem, and that's the very last one that we have. Guys, okay, a lot of people have moved on, and I don't blame you. You're writing exams, and I'm taking your time. I must apologize once again, as I always do. Keep going over the limit, but yeah, you are free to go. So those who are remaining here, okay, I see we've got Hansa, who came in first, Atlakhan, Lulama, Nyuko. Thank you very much for staying till the end, and all the best. I'm not going to see you again for the end of the year, till the end of the year, I think, because I might call upon you again if I'm having some other classes, or the South African Maths Foundation might call upon you. But that wouldn't be now, from now till the end of the exams. And maybe if you're really keen, we can have something in December or something like that. Atla Khan thanks me. Okay, I accept your thanking, and all the best, Atla Khan.